this problem, which is exercise 4.77, is a challenge problem. I like it quite a bit because it really makes us think about, or synthesize a lot of the things that we know, and a lot of things that we've been talking about. Okay, so in this problem we have an ion, which is a charged particle, that travels between two accelerating plates that are some distance apart, but we know that the length of the accelerating plates is 5 centimeters. Okay. We know the distance to the target, and in this problem we're using ion bombardment to treat a tumor. And so what we do is, it turns out that we ramp up in what we call an electric field across the plates, and that actually accelerates the target. So we'd have to remember is that when we put a potential difference across accelerating plates, that what we can do with the ion is we actually can accelerate it in the region. So these are the plates that we're going to be accelerating the particle like this. Okay, so the acceleration is going to be in the positive y direction. Make this positive x direction. And so what we have to do in this problem is we have to recognize a couple things. First of all, if we sort of organize our variables, x and y, here's what we know, okay? We know that at the beginning of the plate, x0 is equal to 0. We know that x final, well, at the end of the plate, so that's when the acceleration takes place, that the final position is 0.05 meters. Now, I do that for a very specific reason here. I'm converting very deliberately into meters so we don't get confused here. All right. And we know that at the beginning of the motion here, that y initial is equal to 0. And it turns out that at the outside, I don't actually know what the final y position is. But it turns out that I'm not going to care either. I don't need to know it for this problem. Because what I'm after here is the acceleration in the y direction. All right, so we're ignoring gravity in this problem. And so, what do I have to recognize about this? So the first thing that I have to recognize is that, so I actually know, and I'm told, what the initial velocity in the x direction is. I'm actually told what that is. And it's 5.0 times 10 to the 6th meters per second. That's fast. That's cooking. Okay. And I also know that the initial velocity in the y direction is going to be 0. Okay, it starts moving in horizontal motion. And, well, I don't know my final velocity in the y direction. I do know my final velocity in the x direction. It's going to be the same, because it's not accelerating in the x direction, because ax is equal to 0. Okay, so my column's got a little wonky here, but this is kind of interesting, right? Because after we get through the plates, right, I have to line up the trajectory such that I hit the edge of the target here, and they said that this is 2 centimeters? Okay, 2.0 centimeters, which is 0.02 meters. And so here's the important thing to realize about this problem, is that after I leave the acceleration plates, I have to travel a distance of 1.5 meters, or the ion does, and the y displacement is 0.02 meters. And so after it goes through the accelerating plates, the acceleration is 0. So whatever trajectory it was on before is the trajectory that it's going to follow. And so it turns out that the final velocity, the total final velocity, has to have components such that we get the exact same angle. Okay, there's no other forces acting on it, therefore there's no more acceleration. And so I know that this is going to be v0x for this component, and v final y for that one. Okay. And so what I can do is I can use this triangle here to help me find the angle, because tangent of the angle is 0.02 meters divided by 1.5 meters. And if I work that out, and if I find the arctangent, I can find that theta is 0.76 degrees. Plug that in. Okay? But that's the angle for the direction of the velocity. Or I know that tangent of theta, same theta, is v final y over v, well, final or initial x. So I now know this, and I know this, which means that v final y is equal to v0x times tangent of theta. So I plug all that in. So I get 5.0 times 10 to the 6th meters per second. Oops, meters per second. Times the tangent of 0.76 degrees. And so what I find for the final y velocity is I end up with 6.6 times 10 to the 4 meters per second. Okay. Okay, so why is that useful? Well, it turns out, okay, that if we struggle through this a bit, and I worked it out on some scrap paper first. This isn't the first time that I'm doing this, but if I know that between the accelerating plates that the acceleration is a constant, which means that I can use the fact that v final y is equal to v initial y plus ay times t. Now this is our guess for constant acceleration motion. Well, I know that. I know this, it's 0. I don't know this, and I don't know the time, but that's okay. Because if I think about the x direction, I know that a good guess for the x direction, now the acceleration is constant, it's 0. x0 plus v0x times time plus 1/2 ax t squared. That's 0. That's 0. Which means that my final position as I get through the accelerating plates is equal to v0x times t. I know this. This is 0.5 or 0.05 meters. The initial velocity in the x direction, well, I know that too. That's 5.0 times 10 to the 6th meters per second times t, which means I can solve for the time. So what I'm going to do here is I'm going to take this expression, v final y is equal to ay times t. I'm going to solve for ay. Ay is v final in the y direction divided by t. I'm going to solve this expression here for t. T is equal to x final, which I know, divided by v0x, which I also know. All right. So this is equal to v final y, which I know, divided by time, so times v0x divided by xf. And so when I plug all of this stuff in here, I get that ay is equal to, plug it in here, okay. Plug it all in, and I get 6.66 times 10 to the 12th meters per second squared, which sounds enormous. Okay, so to give you a sense of this, this is something like 100 billion times gravity. So one of the reasons why we ignore gravity in this problem is this is enormous. But it's also a very small particle. All right, so it's pretty easy to do because the mass of an ion is pretty small. That's the magnitude of ay, so what I would say, I would report that ay is equal to 6.66 times 10 to the 12th meters per second in the positive y hat direction. That's the more appropriate way to report this.